Lesson 2. Shear stress and strain. Axial stress pulled the fibers apart. Shear slides them across each other. 3 one-line ideas. Shear stress is force over the area that resists it. Shear strain is stress over the shear modulus, and the shear modulus ties back to Young's modulus. Then the one distinction that trips people every exam: single versus double shear. Here's the problem. A 20 mm steel pin carries a 40 kN transverse load. Find the average shear stress when the pin is in single shear, then in double shear, then the shear strain. Same pin, same load, but the two arrangements give answers that differ by exactly 2. Understanding that factor of 2 is the point of the whole lesson. Concept 1. Direct shear stress. Where normal stress pulls perpendicular to the cut, shear stress drags parallel to it. Tau equals V over A, the shear force divided by the area that resists it. For a pin sheared across its body, that area is its own cross-section, pi d squared over 4. Same shape as the axial formula, but the load now runs along the plane, not through it. Concept 2. Shear strain and the shear modulus. Push on a block, and it racks into a parallelogram. The little angle it leans through is the shear strain, gamma. It follows the same pattern as before. Strain is stress over modulus. Gamma equals tau over g, where g is the shear modulus, and g is not free. It's fixed by Young's modulus and Poisson's ratio through g equals e over 2 times 1 plus nu. So the shear and axial stiffnesses are 2 views of the same material. Concept 3. Single versus double shear, the crux of the lesson. A lap joint cuts the pin on one plane, so that plane carries the whole load. Tau is V over A. A clevis grips the pin on both sides and cuts it on 2 planes. Each plane carries only half the load, so the stress is V over 2A, exactly half. The pin didn't change. You just counted how many planes are sharing the job. Setup. Build the variable table. The load and the pin diameter up top, the shear modulus looked up, and a blank for each unknown with the formula that fills it. Commit to newtons and millimeters now, so shear stress lands in megapascals with no conversions. And be clear about the area. It's the pin's own cross-section resisting the cut, not the bearing area at the hole. Solve. Part 1. Single shear. Area is pi times d squared divided by 4. Then shear stress is the load over that area. One plane takes the whole load, and newtons over square millimeters give megapascals with no conversion. Part 2. Double shear and strain. Now 2 planes share the load, so the stress is V over 2A, half the single shear value, and you can check it just by having. Shear strain is stress over the shear modulus, the same move as axial strain. 2 planes, half the stress, 1 clean division for the strain. Final answers. Single shear about 127 megapascals. Double shear about 64, exactly half. Shear strain about 1.5 thousandths of a radian. The takeaway: moving the same pin from single to double shear, halve the stress with no change to the part. On the exam, reading the arrangement is half the problem. Traps. 3 ways shear bites. 1. Single versus double shear. Double shear splits the load over 2 planes, so the stress is V over 2A, half of single. Count the planes before dividing. This is the number 1 miss. 2. Average versus maximum. V over A is the average, which is right for pins and bolts, but a beam's shear stress isn't uniform and peaks higher. That's a later lesson, so know which model the problem wants. 3. G is not E. Shear strain uses the shear modulus, not Young's modulus. They're related, but never divide a shear stress by E. Quick recall. Direct shear stress is force over the resisting area. Double shear splits it over 2 planes, so half. Shear strain is stress over the shear modulus, and that modulus links to Young's modulus through G equals E over 2 times 1 plus nu. The golden rule: count the shear planes before you divide. Get those, and the fastener problems are quick points. Next up, Lesson 3. Torsion of shafts. We stop slicing the pin and start twisting it. Torsion makes shear stress 2. Tau equals Tc over J, and it leans on the same shear modulus G you just met, now through the angle of twist. Before then, Redo today's pin at 16 millimeters in double shear under 30 kilonewtons. And practice counting planes. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.